Okay, so what made active transport different than passive transport? Active transport requires energy. Most active transport will actually move something from a low concentration to a high concentration, but not always. How does passive always move? Passive always moves from high concentration to low. There are no exceptions to that rule. Passive always goes like that. Active usually goes from low to high concentration, but there are some exceptions, and we'll talk about those later. All right. Secondary active is probably the most challenging one. This is tough because secondary active means that there are two processes going on at the same time. One of them is a passive form of transport. The other one's an active form of transport. It's secondary. Let me show you. So this is a cell in your GI tract. Here's the lumen of the intestines, the hollow core, and then you have the villi going up and down. Here you have a transporter. This transporter pulls in glucose and sugar. It's like a two-key lock. They have to both be present, and when they're both present, this flips around and brings them both into the cell. If you ate a payday bar and you have all of that sugar and all of that salt in your GI tract, it grabs one of the salts, one of the sugars, and pulls them in. That's high concentration going to low. Technically, that's a form of what? High to low? Passive. But the exception to this is the only reason this is moving is because somewhere else on the cell, like down here on the basolateral membrane, there's a pump that moves sodium. So sodium is being kicked out of the cell where it doesn't want to be, in that extracellular fluid where it's really salty. It kicks the sodium out here through active transport. If you turn off this pump, suddenly the sodium accumulates inside the cell, and it's high concentration in the cell, high concentration out of the cell. What is that? High and high. Equilibrium. Does it want to move? Does sodium want to move now? No. The only reason that sodium's moving from high to low here is because this pump created a low concentration in here. Does that make sense? It's like you have a leak over here pumping out the sodium, and as it's leaking out this door lets it leak back in the other side. It's called secondary active transport. The reason that your cell uses this is because by creating this secondary flow where you're moving sodium this way and pulling sodium in, what's it pulling with it? The glucose. This is how glucose gets transported in. So glucose moves from high concentration down to low, and then glucose moves from high concentration in here down to low in your blood. What is that? Going from high to low. Passive. So technically the glucose moves passively here and passively here, but the sodium doesn't. The sodium moves actively here and passively here. So they call this a secondary active transport. When we get to the GI tract, I'm going to go through this again in better detail, and we'll actually watch sugars being broken down and how they're moving into your bloodstream. So you eat a big sugary meal, that sugar comes pulled in with salt, the salt goes into your blood, the sugar goes in your blood pressure goes up just a little bit, and your blood sugar goes up a bit. Right. And then the last types of transporter are vesicular transport. So vesicular transport means it uses this little tiny vesicle. We talked about this when we talked about the organelles. The vesicles are the little things that move around in the cell carrying products. And there are two major types. There's endo and exocytosis. Where's it going if it's exocytosis? Out. If it's endo, it's being pulled in. All right, and then I thought there were two more on here. We talked about this already, didn't we? Pino and phagocytosis. Phago means to eat, so you eat big particles. What's the one that has small particles? Pinocytosis, which means to drink. So this is like an in-depth question. You won't see a question like this on a test, but think about it. See if you can put the pieces together and figure out what type of transporter or what type of movement this is. So given that a transport process exhibits saturation, in other words, you can plug it up. Poisons that block metabolism, like energy production, don't affect it. So it doesn't matter if you have ATP. And the movement is always from high to low concentration. Is the transport process a form of diffusion, facilitated diffusion, active transport, secondary active, or a bulk transport like vesicular transport? Take it one step at a time. If it can be saturated, does that mean that you have a transporter for it? Can you saturate oxygen? Can you saturate in the cell? Oxygen will just keep flowing through, and your cell keeps putting in energy and just keeps flowing. There's nothing limiting oxygen's flow. It can't be saturated. When I talked about this last week, I talked about like glucose. Glucose can only move so fast because you have little transporters. Otherwise, they get saturated. Does anybody remember that? I talked about saturation, competition. Nobody remembers. So in this situation, you have to have a transporter. So is it just diffusion? It's what type of diffusion? It's at least going to be some kind of transporter like facilitated. Is it going to be facilitated diffusion, or is it going to be an active form of diffusion, or active form of transport? So is it facilitated diffusion or active transport? Look at the next line. Mechanisms that block ATP don't affect the movement. Does facilitated diffusion need ATP? Doesn't have to. Does active movement have to have ATP? Yes. So if you blocked ATP, what would happen to active movement? If you couldn't make ATP, active movement stops. So you know it's not any of the forms of active, not secondary active, not bulk, so what's it have to be? It has to be facilitated. There's a transporter, and ATP isn't important. Facilitated diffusion. And what else tells you it's some form of diffusion? Movement is always high to low. Yep. If it's high to low, it's always going to be some form of diffusion. So we talked about this last week, which is the following diffusible factors are dependent on concentration gradient. Was pH important? Does acid move from high to low? If I put acid in the side of the bathtub, will it stay over there? Will it move from the high concentration to the low concentration until it's at equilibrium? Yep, so that moves on diffusion. How about temperature? Can I put a box of hot right there and keep it there? No, it'll move. That heat from that box will move across the room. Is that diffusion? Going from high temperature to low temperature? High concentration of heat to low concentration of heat? It's diffusion. How about if I put a bunch of positive ions on that side of the room? Will they stay over there? They'll diffuse downstream. How about if molecules like perfume? If I spritz a bunch of perfume over here, will it stay there? Nope. How about water? Does it go from high to low? Does it move on a concentration gradient? Yeah, what's the process of it moving high to low? Osmosis. So all of these things move on a concentration gradient. You do too. If it's too crowded in here, where do you want to be? Yeah, obviously not today. You're happy to be in here because that hallway's so cramped. But big concept is everything in the world moves, actually everything in the universe moves from high to low concentration. Everything diffuses. Right? Which of these pictures would show a hypertonic solution? So this is a red blood cell, right? If this red blood cell looks normal, what kind of solution is it in? ISO. If it looks like a raisin, what's it in? Hyper. If it looks like a gigantic swollen up, about to burst red blood cell, it's hypotonic. All right. Substance moves from high to low concentration through an impermeable membrane to that substance. How would it get across? If it's an impermeable membrane, what's it have to help it across? It has to have a transporter. So would it be just simple diffusion? Nope. If it's moving from high to low, would it be a form of diffusion, or would it be an active diffusion? What's wrong with that first one, active diffusion? There's no such thing. It's telling you exact opposite. Active means that you're putting energy into it. Diffusion means you're not putting energy into it. Active transport requires what? Energy. How about through a protein pore? If it's moving through an impermeable membrane through something special, is it a protein pore? Or a protein channel? Or a protein transporter? Or a protein anything? Yes. So what's the correct answer on this one? Facilitated diffusion is one of them. Protein pore is another. What's the right answer? More than one. I'm hitting you with as tough of things as I can right now, so that when you get the test, you're like, oh my god, this is so easy. I hope you think that. All right, membrane potential. Charge in the form of ions builds a membrane potential. This is back into your notes again. This is not review anymore. When you put that membrane around the outside of the cell is its own little biosphere. It uses positive and negative charges to create electricity to generate things like energy, like ATP. When you separate negatives from positives, we call it a membrane potential. If you see a positive charge, it's also known as a cation. The way I always remember this is that the cation has this T that looks like a positive, where the anion doesn't have anything. There's no negative in it, there's no positive in it, but the cation has a positive T right there in the middle. So what is sodium? Na plus. Yep, Na positive. How about chloride? Cl minus. How about potassium? K plus. Yep. So what would potassium be? An anion or a cation? Cation. What would chloride be? Anion. What would sodium be? Cation. How about calcium? Ca plus plus. Two pluses. What's that? It's a cation. Yeah. Okay. Some cells will use that special charge for special purposes like the neuron. This line here I don't think is in your notes, but today we're going to shift over and we're going to specifically start talking about a neuron and how it manipulates that action potential, or that electricity in something called an action potential. So if I were to create the inside of a cell here and the outside of a cell here with that membrane, if you look over here, you've got 15 positives on this side. On this side, you only have 5 positives. Where does the positive naturally want to go? Does it want to go over to the left, or does it want to go over to the right? It wants to go to the right. It's going to work based on its concentration gradient too. It's going to move downstream. How about the negatives? You have 10 here and 10 here. Where's negative want to go? It wants to stay. It's at equilibrium. It's comfortable right there. So don't get tricked. I know a lot of times if you've taken physics classes, they always say that the positive wants to go to where the negative is. But just think of it this way. It's possible that you have a lot of negatives in one area, 10 of them, a lot of negatives in this area, 10 of them. Does the negative want to move? It doesn't want to do anything. But if you have positives that are high here and low here, where's the positive want to go? Down its gradient. And your cell's going to be like that. It's going to start building up lots and lots of negatives on the inside. So if this is the cell, you can see that whole plasma membrane going around. Just on the inside, it's crisscrossed. Plus, minus, plus, minus, plus, minus, plus, minus. But there's so many extra minuses that it lines them all up along the membrane. They're kind of like wallflowers. On the outside, you've got the same pattern, plus, minus, but there's so many extra pluses out here, they line up along the membrane. So can a positively charged something just diffuse across the membrane? No, because it's polar and it likes what? Water. It can't slide through that lipid membrane. So they stay like this. What you're going to do, or what the cell's going to do, is it's going to put what kind of transporters made out of what? Lipids, proteins, or carbs? What kind of transporters? Lipids, proteins, or carbs? Carbs for recognition, lipids were the fluidy bilayer, and then what did proteins do? Like everything else. Transporters, receptors, enzymes, all of those. So you've got this little protein transporter here that's called a protein pump we're going to talk about. You have to have it. The next thing you have to put stars by are these, sodium and potassium. Where's sodium most abundant at? Inside the cell or out? Out. So the extracellular fluid, you can see 150 particles versus the intracellular fluid, only 15. What about potassium? Where's it most abundant at? Inside or out? Inside the cell. Inside the cell is 150, outside the cell has 5. Huge difference. The way I always remembered this is I imagine the cell being a little island. Did I tell you this already? So the cell's like a little island with lots of banana trees on it. Why banana trees on the island? Potassium. The island's full of potassium, so you have this potassium island floating here. What's the island usually surrounded by? What kind of water? Usually associate islands with salt water, right? What is salt? Sodium and chloride. So you have lots of sodium and lots of chloride out here, but lots of potassium in here on the inside. This last A negative means protein anions, bless you. On that island, all of that substance, that thick substance, are all piles of protein on the island. So you've got lots of negative proteins, you've got lots of those positive banana trees. Out here you have the negative chloride and this positive sodium. Sodium plus chloride is table salt on your table that you shake on your food. Okay, this equation is a nightmare. This is what happens when you get a bunch of scientists together with a bunch of mathematicians, and they go, how can we make life miserable on people studying this? And they come up with the Nernst equation. The Nernst equation, what you have to know from this, is it takes the electrical potential of an element, and it takes the chemical properties of the element, mixes them together, and determines where the element wants to go. So think of it this way. If I have potassium. Potassium is high where? Inside or out? It's high inside the cell. You have a big pile of potassium inside the cell. The chemical potassium wants to stay in the cell. Where did I tell you it's more negative at? Inside or outside the cell? outside the cell. See all the positive charges? What charge is on potassium? K plus. So you've got this positive potassium. Potassium's electrical component is a positive. Does it want to go out here where it's really crowded and positive? No. Potassium split. The Nernst equation was put together to explain where potassium goes because of this split. Potassium wants to go out of the cell because of its chemical properties, but it wants to go into the cell or stay in the cell because of its electrical properties. So if I open a doorway to potassium, is it going to run across that membrane, or is it going to be confused and move very slowly? It's confused. It doesn't know where to go. If I put 500 people in this room, do you feel crowded? Yes. What if I open that door? What do you want to do? You might want to go out, but what if there are 499 people out there? You still want to go out? Maybe there are fewer people out there, but as soon as you're out there, then what happens? It's actually more crowded out there. You understand? So potassium's like that. It wants to leave the crowded cell, but its electrical properties are going, man, but it's so positive outside, and I'm a positive. It's just going to be so crowded with the positives out there. So the key you want to write down somewhere in your notes is that if you open a doorway to potassium, potassium will move out of the cell, but it will move very slowly. Potassium slowly moves out of the cell. Does that make sense? Think about sodium. Where's sodium most abundant at? Sodium is most abundant outside the salt water, remember? There's a lot of sodium out here. There's barely any sodium in there. If I open the door to sodium, where does it want to go? Inside. What's sodium's charge? Positive. Sodium's a positive. So based on the positive charge, where does sodium want to go? Does it want to go inside or stay outside? It wants to go in. It's so crowded with positive charges out here. If you open a door for a positive charge, it goes in. Everything. Sodium's chemical properties and sodium's electrical properties both want it to go where? In the cell. If I open a door, is it going to move slowly like potassium? Everything about sodium says go into the cell. So how is it going to move? Slowly? Fast. As soon as you open a sodium door, sodium charges into the cell. It doesn't hesitate at all. It just starts flying into the cell. Everything about sodium says go into the cell. The Nernst equation, like I said, is taking all the mathematical qualities of electricity and mathematical qualities of the chemical, mixing them together, throwing a little logarithm in there, putting some division and some little sub numbers under it, just to make it look tricky and nasty, and telling you sodium goes where? Into the cell very fast. Potassium goes where? Out of the cell very slow. The end. That's the last you'll hear of the Nernst equation. In this class. If you go into like a molecular biology or you go into something more in-depth than this class, then they may have you know it then. But what you need to know, and every time, whether I've taken the MCAT or any exam in other classes, grad school, undergrad, the only times that Nernst equation popped up is they wanted to know the overall function of it, what the overall thing that happens to potassium or the overall thing that happens to sodium or chloride or calcium. And as we're going through this and I'm introducing each of these ions, I'll tell you what they do based on the Nernst equation. What's your gut tell you about chloride that's out here? Chloride has a what charge on it? A negative charge. If I open the doorway, does chloride want to go in? It doesn't. But chloride is so abundant in salt water that it's like potassium. It's torn. Chloride wants to go in based on its chemical properties, but it doesn't want to go in based on its negative. So if I open a doorway to chloride, what's it do? Does it rush in, or does it slowly move in? Slowly. It slowly moves in. Yeah, we'll stay with those three for right now. And as we need it, I'll introduce the other ones. So the Nernst equation, you need to know that it's the electrical and the chemical properties that are telling you where things move. The next thing you want to know is sodium always moves into the cell extremely fast. Potassium moves out of the cell very slow. Chloride moves into the cell very slow, just like potassium, except the opposite. Okay, so that membrane potential, how it stays negative on the inside. 80% of that membrane potential is because of passive diffusion. There are just a few little doorways that are stuck open so that sodium and potassium can move. but barely any. When you look at the slide back here and it says the permeability, look at sodium. Sodium is virtually impermeable. So even though there's one there, you can say in your mind it's impermeable. Sodium doesn't move easily. Does potassium move? Yep, there's some permeability in there. 50 to 75 times more permeability. So potassium can leak back and forth. So 80% of this change or this quality is that potassium's taking its positive charge out of the cell. If you have a 0 in here and you start taking positives away from 0, what do you get? Here's your fun math. Simple math, how do you make simple math really difficult? What is 0 minus 10 positives? It's negative 10. It's negative 10. If these doorways are open for potassium and you leak 70 potassiums out, what's it make the inside? It takes 70 positive charges out of the inside of the cell, which makes it negative 70. So the inside of the cell, you want to have somewhere written down negative 70. And MV is the actual units, called millivolts. And then the last thing that creates that membrane potential is something called a sodium-potassium pump. Guess what two ions it moves? Sodium, potassium. Guess how it moves? If it's a pump, is it passive or active transport? It's active. Pumps require energy. I would underline this. The pump moves 3 sodiums out. Where does sodium want to go naturally? It wants to go in. You put energy into moving it where? Out, where it doesn't want to be. So it moves 3 sodiums out. And then at the same time, it kicks 2 potassiums back in. 3 sodiums out, 2 potassiums in. Think about that math. If I take 3 positive charges out of the cell, and then I add 2 positive charges back, what's my overall difference? Negative 1. So the inside of the cell has a negative 1 because of this pump. So you can see that there are 2 processes creating that negative charge or that negative membrane potential on the inside of the cell. Right? So overall, therefore, the outside is more positive than the inside at rest. And your book shows little pictures. You can see the potassium leaking. Intracellular fluid, potassium leaks out. These big proteins, they're big proteins. Why are they not leaving? Because they're too big. They're big and bulky. They can't fit through that membrane. What's the other thing that keeps them from moving across the membrane? This is a non-polar membrane. What about this is not letting it move? It loves water. It has a charge. It's polar. It has a charge. And then sodium wants to go into the cell. It just can't easily. What about chloride? Where's chloride want to go? Shoo, into the cell. A general rule of thumb is wherever sodium goes, chloride wants to too. They're buddies. You put them on your table, they stick together, right? They form table salt. They always like to be together. If one's pouring into the cell, the other one wants to go. If a transporter allows sodium to go through, though, transporters are specific. Will chloride get to go? Nope. Specific. It's very specific to sodium. So if I want chloride in, what do I have to do? I have to open a door that's specific to chloride. So if sodium goes in, chloride just hangs out here along the membrane, looks and waits for sodium, all lonely and sad, like my dog sitting at the window when I drive away for work. Right? I have a seat in the car. Why didn't I get to go? But sodium and chloride, they always want to hang out together. So if the transporters allow chloride to move in and another transporter allows sodium to go in, they'll go together. We'll talk about that later when we get to the GI tract, because their GI tract will actually pull sodium and chloride both in at the same time. All right, and then here are the transporters. So here you can have a passive transporter. How do you know this is passive? Look at the concentration here and the concentration here. Large concentration, small. How's it moving? High to low. It's passive. Okay. How about potassium? Intracellular fluid's high concentration, extracellular is low. How's it moving right here? From high going down to the low, which is passive. What would this thing be then that's moving them where they don't want to go? Look, it's taking sodium and pushing sodium out of the cell. Sodium doesn't want to go out of the cell. It's taking potassium and pushing potassium into the cell where it doesn't want to be. What is this? That's the active thing that spins around called a, sucks water out of my basement, pump. Right, so if I asked you this question on an exam, which of the following is true for a cell at rest? Whoops. I just screwed that up. That's better. Sodium is found in highest concentration outside the cell. I hate it when I stutter on paper. Is that true or false? Sodium is found in highest concentration outside the cell. Where's sodium primarily at? Outside the cell. How do you know that? Because the cell is surrounded by salt water, which is sodium and chloride. So that one looks true. Do you want to stop there? No, read the next one. Because what could the last one be? All of the above, right? So number 1 looks true. How about number 2? Potassium is found in highest concentration outside the cell. Where's potassium highest at? Inside. Cross that one out. Number 3, or put a false by it, whatever you want. Number 3, potassium is leaking into the cell. If potassium is leaking, where's it leaking to? Outside. If it leaks, it moves by diffusion. So it leaks out of the cell. That one's false. How about number 4? Negatively charged proteins leak out of the cell. That's false. Those anion proteins, they can't move through. Why? They're big and they have a charge. So that membrane, that lipid membrane, doesn't let them go through. That one's false. How about at rest, sodium is leaking into the cell? I said sodium is practically 0. So is it actually leaking into the cell? No. So we're going with number 1, which is sodium is founded, highest outside. Let's see if this works. It doesn't. Okay, being really difficult here. I always get a little nervous when I open up anything on these computers that requires the internet because it's usually so stinking slow. There we go. Uh-oh. So here are neurons, and this is showing how neurons manipulate that membrane potential. We're looking in really close to the neuron. And then there are those little channels, those pores. So here's the inside. What's highest inside? Potassium. What's highest outside? Sodium. If I open up a pore, I don't know which one's going to pop open first, actually. So negatives on the inside, positive outside. What's the negative value on the inside at rest? Negative 70. And come on, you. So what should it be? Yep, it should be negative 70. And then you look at, there's the phospholipids. Here's a protein channel. Don't know why the sound's not working. All right, where does sodium want to go? Inside. It wants to leak down its gradient and go inside the cell. Where's potassium want to go? Outside. Is this a realistic speed of movement? No, because what do you know about sodium compared to potassium? You open a couple sodium channels and it flies in, it pours in as fast as it possibly can. These are called leak channels because they're always stuck open. And then you can see the movement. And come on, you. So if I start changing this membrane, if I manipulate it just a little bit and I block the sodium, you can see that potassium keeps moving out, and potassium takes more positives out of the cell, making it more negative on the inside. The neuron manipulates this to try and act like a battery and change the charge or the power that's going back and forth through it. What would happen if I plugged up all the potassium channels and just let sodium move? The inside of the cell would become more positive. And then there's the sodium-potassium pump. Here you can see 2 potassiums being pushed in where they don't want to go, 3 sodiums being pushed out. What was that little flash? What do you think that little flash is? Did you see it? It's just like in your car when your engine's running. Guess what's happening inside the engine? You're burning energy. So there's that little energy burn, poof, and then it creates that movement. And then you strike another one, creates more movement, and it keeps doing that back and forth. So overall, you have all these leak channels and all of this sodium-potassium pump that are shifting things back and forth. And that neuron's going to use that to create energy, or an electrical potential, which is the next thing we're talking about. All right, so big concept to take home here is that the cell has this membrane potential, which means it creates more negative on the inside, more positive on the outside, so that it can get excited and do something like create electricity. I would put a little line above there. Now we're shifting into the neuron. This is next in your notes, right? A couple of you look a little confused, so I put a line above this. When you trigger a cell, when you try and create an electrical charge, or you try and create something active in the cell, you have to have a triggering event. And the triggering event can be any kind of stimulus. Just anything. You can poke a cell, and that'll stimulate it. You probably heard when people will open up like a doctor will open, not any person, but a doctor will open up somebody's chest and actually massage the heart. They're stimulating those cells to try and get them to keep moving. Oops. All right, next thing that can happen is a change in electrical field around the membrane. You don't actually have to touch the membrane, but if you change electricity around it, it'll change that cell's little doorways. If you want to try this, if you go to the sanitarium, I don't even know if they call it a sanitarium anymore, but anyway, if you go there, you get the electrodes hooked up to your head and they send electricity through you, they recharge everything. What is that? Electric shock therapy. Or if your heart stops, they can put electrodes on your heart and do what to it? Shock it. They try and shock it back into rhythm. They kickstart these cells and try and get them to fire again. So it doesn't even actually have to be touching the heart, just the electricity around it can change this. And the heart cells get excited and they change their membrane potential and start firing again. Interaction of a chemical messenger, so you want to think of the endocrine system here typically, or a neurotransmitter. So hormones and neurotransmitters. If I dump adrenaline into my blood, that adrenaline goes down to the cells, to the target cells, and it opens little doorways for sodium. Sodium goes in and excites those cells, gets them all crazy. Number 4, spontaneous change of potential because of inherent imbalances. In other words, the cell's not perfect. The cell's not always going to stay perfectly at 70. It may stagger a little and go to 75. It may go up to 65 and then back down to 75. Then it might go to 70 a little bit and then stagger back and forth. Sometimes it just happens. If the cell's not getting oxygen, it can't make what? Well, it can't make it efficiently. What organelle is depending on the oxygen? The mitochondria that makes ATP. If you can't make ATP, like for instance when you're having a heart attack, if your artery gets clogged and deprives the heart muscle of oxygen, those mitochondria suffer. They can't make ATP. What happens to the pumps? What happens to the pumps in those heart cells? They stop because they're missing. Or if you don't pay your electricity bill, I turn off your power, what happens to your pump in your basement? It stops. If you don't give oxygen to the mitochondria, it can't make ATP, and those pumps stop. Water starts flooding into the heart cells, and if it keeps flooding for too long, guess what happens to them? They start lysing. They start breaking. Water's flowing in, they expand, they burst. Guess what you're having? A heart attack. That's why after somebody has a heart attack, we take a sample of their blood, and what we're doing is we're testing for the chemicals that normally should be inside of a heart cell. They burst, and now they're flowing through their blood. All of these disrupt the membrane potential, all those points. So here's how it might work. I get really close to a cell and I bump it. Bink! I bump that little sodium channel. It opens up and sodium goes rushing in. As sodium rushes in, it's going to neutralize these negative charges. And it's going to move down that membrane and start changing these one at a time. Moving away from the central source. Floods in, change. Hopefully there are pumps over here that pump that sodium back out so that I don't get a change far down the road. But changes. So because there are pumps all the way along here, some sodium is going to get pumped out here, some sodium gets pumped out here, some gets pumped out here, until now I'm back to normal. I get the major change here, and then the further I get away from that site, the less change I have, because the sodium is being pumped back where it doesn't want to be, which is outside the cell. All right, 2 types of electrical signals we're going to talk about. One's called gradient and one's called an action potential. Graded potential means they vary, is the simplest way to think about it. If you get electrical activity in a cell and it's graded, it can be a little activity, it can be a lot. It can be medium, it can be semi-medium, it can be semi-large. It can be all kinds of different changes. And action potential right next to it, always the same every time. Yeah, I'm being redundant. Always and every time. Because there aren't any exceptions to it. It's always exactly the same. Graded potentials, do they vary? Yes, they do. The big thing that separates a graded and action potential is one varies, one never changes. One is always exactly the same. Okay. So what you need to know about graded potential, this is in the notes, right? So you don't have to write it all down? Perfect. All right. So one thing is they're local. I would underline local. What I mean by that is if this entire room is a cell, we're all inside this cell, and I do this, can you hear me tapping? Can you hear me tapping in the back? It's local. Only the people close or local to it can hear it. That's local. You have a local change. If I tap a little bit harder, people in the second row can hear. If I tap a little bit harder, people in the third row can hear. Tap a little bit harder, people in the fourth row can hear. And if I finally start doing this, everybody can hear. By the way, when I do this, it's no longer graded. Now it's in action potential. Because I can't hit any harder than that. It's always the same every time. Graded are always local. Little local changes to wherever that's happening. Next is it goes a short distance. If this membrane, if this wall were a lipidy membrane and I do this, what would happen? It would go bloop, kind of like a puddle. It goes bloop, and then it recovers. What if I hit it a little bit harder? You see that wave go a little bit further out. But they're short distances. So wherever you affect that cell, if I poke the cell on this side, it just changes this area on this side. If I poke it a little harder, it goes a little bit further, but still a short distance. Okay. So local changes, I already said local. So local change in membrane potential, local current flow. It moves from the most active area to the least active. Same thing here. The most active area is where I'm putting my hand on the wall. The least active is where I'm not putting my hand. So that movement goes from the most active where I'm pushing, and it kind of goes like a wave out here to the least active. It always moves away from the source. And then the magnitude of the potential decreases as you get farther away, and I already mentioned this kind of. The further away that ripple is, it starts moving back to smooth water or smooth lipid. The stronger the event, the larger the graded potential, and some of the examples we'll talk about this semester are called postsynaptic potentials, receptor potentials, end plate potentials, pacemaker potentials, slow wave potentials, and the only one that doesn't fit in this is called an action potential. So when you see an action potential, does it change? Every time you see an action potential, what can you count on? It is exactly the same every time. If I look at graded, you can see here's a small graded potential, a little bump. Here's a bigger one. There's a bigger one. They change. They vary. If I stimulate the cell right here in the middle, this is where I get the most change. The further away, I get least and least change until there's no change at all. And action potential, these are the things you want to know. First is that rapid. Look how long it lasts. 1 millisecond. 1,000th of a second. As fast as I can even think about 1,000th of a second. All right? So extremely brief. It has rapid reversal. It comes and goes. In other words, it turns on and off extremely fast. Like if I flip the light switch off and on, it's fast. But it happens in 1 millisecond. Extremely fast. The next thing is that it doesn't decrease. This thing, if I smack it here, every time I hit it, it's powerful enough that the ripple goes all the way along this wall, down those walls, across the back wall, it makes a change in the entire cell. Every time that I get an action potential, it changes the entire cell. The whole cell changes. These are the stages or the steps of an action potential. So when we describe an action potential or we describe a cell, we say it's polar. Because one side of the membrane is negative, the other side of the membrane is positive. So it has polarization or polarity. If I depolarize it, what am I doing? I'm taking it from negative 70 to what? What would make it have no polarity? If it were at 0, right? So when you're depolarizing, you're bringing it to 0. From negative 70 to 0 is depolarization. If I go from negative 70 to negative 65, that's depolarizing. Negative 70 to negative 40, that's depolarizing. Negative 70 to negative 1, that's depolarizing. I'm moving it closer to removing its polarity. If I repolarize it, what am I doing? I'm moving it from where to where? I'm moving it back to negative 70. So maybe I'm going from 0 to negative 70. Maybe I'm going from 10 to negative 70. Maybe I'm going negative 10 to negative 70. Maybe I'm going negative 69 to negative 70. That's repolarizing. I'm bringing it back to its rest. Depolarize is taking it from rest to 0. Repolarize is going from anything back to rest. And this last one is hyperpolar. What did I just do? I made it, what's hyper referring to? More than, excessive, beyond, right? Hyper, I just made it more polar than it normally should have been. So where may I have taken it? Negative 71, negative 80, negative 90, negative 100, negative anything more negative than 70. Negative 70. So if I drew them, they would be like this. Here's my resting at negative 70. If I depolarize and bring it maybe up here to negative 60, when I bring it back to negative 70, I'm repolarizing, and then I'm at rest. And then suddenly I take it and make it hyperpolar, which is negative 80 in this example, and then I bring it back to rest. So you can see this thing wobbles a little bit back and forth. One of the things that causes a change would be a voltage-gated channel. Voltage-gated channels. Voltage-gated channels are stimulated by voltage, electricity. If I bring my car battery in, sit it on this table, and I hook it up to you, I will open all the voltage-gated channels in your body. They all open. They're stimulated by electricity. If I kickstart your heart, I put that electricity on your body, it goes down to the heart and it resets it. It goes to the brain and resets the brain too. If I put those electrodes on your temples for electric shock therapy, send that charge to your brain, I reset. I open all those voltage-gated channels and I reset everything. So they're found in the membrane and they're sensitive especially to two ions that we're going to talk about now, sodium and potassium. Later we'll talk about some other ions they're sensitive to, but right now you want to think sodium and potassium. Maybe that's somebody pushing back on the wall. Did everybody hear that? Oh. I was going to say that's a good example of a graded potential right there, but I guess not. Everybody heard it. It's an action potential. Okay, this word conformational means shape. It's a fancy word that's in the book, and it means shape. When something goes through a conformational change, when you take the clear part of an egg and you cook it, you're denaturing it, and it goes through a conformational change. It changes to a new shape. Some things can change back. Will the egg change back? No. But this can. This voltage-gated channel, let's say that it's like this right now. It's shut, it's closed, and then I send electricity through it and it goes whoop! Now can anything slide through? Yep. If this is a sodium voltage-gated channel, what slides through? Just sodium. If it's potassium, it's just potassium. And then as soon as I take the electricity away, it goes whoop! And shuts again. Can the sodium keep moving through? Nope. So when you expose it to voltage, it pops open. You take the voltage away, it closes. And it just keeps doing that back and forth as long as the electricity is there. Voltage-gated channels. So how do we manipulate these things? How do we get an action potential? We're going to use those voltage-gated channels. We're going to talk about depolarization, hyperpolarization. We're going to put all these things together now. Anytime you see a list of events in order, you should put a star by it, by the way. This is physiology. Physiology is a process. It's the process of how things work in your body. It's not just saying that's a muscle. It's how the muscle works. Step 1, I send a neuron to the muscle. Step 2, it releases neurotransmitter. Step 3, blah, blah, blah. Steps of an action potential start with some triggering event that we just talked about. It can be an electrical change in the area. It can be a stimulus poking. So some kind of a triggering event. The next thing that's going to happen is it starts depolarizing. When you trigger that trigger event stimulates the neuron or the muscle cell or the cell in general. Now it's going to start depolarizing. It's going to open up little channels for sodium. What does sodium want to do? Does it want to go out or want to go in? It goes in. If sodium is bringing positive charges into a negative environment, let's say 10 sodiums come in. What's that do to the negative 70? Negative 70 plus 10, negative 60, right? So if you take negative 70 and add 10 to it, it brings it up to a negative 60. So that's depolarization. The next word you want to underline is the word threshold. Your goal to try and get an actual potential is you have to hit threshold. Threshold for a cell is typically negative 50 to negative 55, depending on the cell. Anybody here have a little sibling that when you were small, they would come up to you and go, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. You're okay with it until you hit your threshold. At that point, you do something about it. If you take a cell and you poke it and poke it and poke it and go ha ha ha, and you keep letting sodium leak in, at this point when it hits negative 50 or negative 55, suddenly it hits threshold, it says I've had enough. It fires an action potential, which is like a bullet. It fires this action potential bullet. Can you take it back once you pull the trigger? Nope. At this point, you're committed. You've depolarized enough that you hit threshold. Threshold means you're committed to following through with an action potential. Can I get a big action potential? A small one? Every time I get an action potential, what do I get? An action potential. It's never big, it's never small. As soon as I hit threshold, it's always exactly the same. So this is what happens. At threshold, you get an explosive depolarization. Suddenly, every sodium voltage channel opens. What's sodium going to do now? It doesn't just slowly leak in. What's it going to do? It's going to fly in as fast as it can possibly move, right? Every door is open. If I throw a grenade in the middle of the room, what's going to happen to every one of these doors? You're going to open every one of them and you're going to rush out really quick. That's what sodium does, except just the opposite. It rushes in, right? It's going to rush out so fast that this is kind of interesting. It doesn't go back to negative positive zero. It doesn't go back to zero. It actually goes beyond zero, and it moves into the positive area. Let me show you. Like this. Here's your negative 70. Step one, I do some kind of triggering event. I poke the cell. It starts letting sodium in, kind of slow. Sodium's moving in. Right? Once I hit this negative 50, which is threshold, I open every sodium channel. Look at what sodium does. Instead of creeping in like that, every channel's open, it flies in really, really quick. Until so much came in that the cell goes, holy crap, we're comfortable at negative 70. Now suddenly, we're exactly the opposite. It's like turning the cell's inside out. It's uncomfortable. So the cell's so uncomfortable, what's it going to do to all the sodium doors? Close every one of them. It closes absolutely every single sodium doorway. Is sodium moving anymore? If I close every doorway, absolutely not. It's not moving at all. So what can I do? What can I do to make the inside more negative again? If I can't move sodium, what can I move? Potassium. If I open doorways to potassium, where's potassium go? Potassium goes out. It rushes out, taking its positive charge with it. So now suddenly every potassium door is open. Potassium's running out and taking its positive charge, making the inside of the cell more negative, 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 negative. Until I hit resting again, did it stop? The doorways for potassium are old and rusty. The sodium doors are quick. They pop open, they pop shut. But when you go to shut a potassium door, when it hits rest, it goes, okay, we're done. It goes, eee. Can potassium still move through that while it's slowly shutting? Yes. So potassium keeps leaking in and actually makes the cell, what's this purple area called? More polar than it should be. Hyperpolar. So it makes it hyperpolar, and then that sodium-potassium pump brings everything back to balance, and what's this called? Resting potential. So if you put those steps together, you can actually see each of them. So why it occurs, and I actually walked you through this too. The last one were the steps that happen. This is why each of the steps happen. So the resting potential, you've got, like we've already talked about, you have the potassium channels that are open and leaking, but then the sodium channels, they're closed. Then I have a triggering event that allows what to move? Sodium. I would underline sodium. Sodium is always, for the sake of what we're talking about now, it's always going to be sodium repeatedly that's causing depolarization. When we get to the cardiovascular system, we're talking about special cardiac cells, this will change just a little bit. But sodium's coming in. When you hit threshold, what are you committed to now? An action potential. So at threshold, what happens to the sodium doors? Every single one of them opens. All those voltage gated doors open. The voltage inside the cell changed so much that every voltage door went through its conformational change, and now sodium's flooding. What number did that change? So I went to threshold potential, and now I'm rapidly depolarizing until I hit what number? Positive 30. At positive 30, what happens to every sodium door? Shuts. So sodium channels close. Every sodium door shuts. What channels open? Potassium. Potassium opens, and potassium goes where? Out. So it's flooding out of the cell as fast as potassium can carry itself. It makes the inside of the cell more and more negative until it actually overshoots, called hyperpolarization, and then you bring back to resting. So my piece of advice, I would take both of the last sections, the one that had the 5 or 6 events, and then the one that talks about the ions that are moving, and just combine them. Just say, step 1, triggering event, allows some sodium to come in. Step 2, you hit threshold, opening all sodium doors. Up at the top, you have a peak at positive 30, closing all the sodium doors, opening all the potassium doors. Potassium rushes out, causing repolarization. Down at the very end, potassium causes hyperpolarization until all of the potassium doors are shut and the pump rebalances it. These voltage doors, by the way, are awesome. It's so cool. These little tiny gates, there are thousands of them on one cell, but the way they're designed is just like miraculous. So sodium at rest, when the cell's at rest, sodium can't get in because the doorway's shut. But this has 2 doorways, or what they call gates. You have one that's the first, or the primary doorway, and you have this backup doorway just in case. Suddenly the inside of the cell starts changing its polarity, and that first gate pops open. Can sodium move? Absolutely. Sodium's flooding in. It's flying in. But then when the inside of this gets so positive, this has a positive charge on it. What do all these positive charges want to do to that thing? They want to try and push it out, right? So look how big it is. Is it going to fit out? Nope. So it just goes like a plunger. You know, like when you pull the plug in the bathtub and you put the plunger in, it works its way back over and then stops it up and stops all the water flowing. It's the same thing here. When you put too many positives in here, that little plunger starts shifting over and then whoop, plugs up the hole and no more sodium flows. Stops the sodium flow. Potassium's kind of like that, except potassium doesn't have the backup plunger, right? Which explains why sodium's so fast to stop, is because it has that little wiry plunger. Whoop. I love that sound, so I just keep making it over and over again. But potassium doesn't have it. So potassium, you have to wait for that door to creak shut. So if you're looking at the electricity in a cell, here you see resting. What do you notice about both doorways? They're both closed. Both voltage-gated channels are closed for sodium or for potassium. Then suddenly, let's say I change this, and I depolarize this just a little bit to pop open that voltage channel. Dink! What's going to happen to sodium? Sodium starts rushing in. Sodium rushes in. What's happening to the cell? It's depolarizing. Look at all the sodium start flying in, but when it gets up to this positive 30, what's going to happen? Yep, it floods in, and then at positive 30, look, that plunger shuts, it goes bink, and pops back in. Makes a new sound now because it's not as excited. But look at the potassium gate. Potassium starts creeping open. What's going to happen to potassium? Flows out. Potassium goes flying out of the cell. Look at it go. Now it's dropping, 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 and when we hit resting, look what happens to these 2 doorways in sodium. They don't ever reopen during this phase. They just kind of rub against each other so that no sodium can leak until they're both reset. So they just do that shifting. So they're never open enough that sodium can actually leak. But potassium's still leaking, causing you to hyperpolarize. And then what's going to happen to potassium down here? Potassium channel is going to shut. Yeah. So it's completely closed, and then the pump brings us back to resting. Like that. So you should be able to draw this in your sleep. Just saying. Knowing sodium comes in, causing depolarization at the peak, sodium channels close, potassium channels open, causing repolarization, and then hyperpolarization because potassium channels are slow to reclose. And then the sodium-potassium pump gradually restores that concentration difference brings it back to norm. And you already know the sodium's pumped into the extracellular. How many sodiums are pumped? 3. How many potassiums are pumped? 2. So what causes repolarization in an action potential? What causes repolarization? How many people think it's number 1? Sodium enters the cell. True or false? When sodium enters, what's it causing? Depolarization. We know that one's wrong. Number 2, sodium leaves the cell. What do you know about all of the sodium channels during repolarization? They're all closed. So is sodium leaving the cell? Nope. How about potassium enters the cell? Does potassium want to go into the cell? Nope. Potassium wants to go out. How about number 4? Potassium leaves the cell. Yes, that was true to me. How about number 5? Proteins leave the cell. They never do. The only time proteins leave the cell is when you smash the cell. Remember the myoglobin story? When you cook a cell and you destroy its membrane, the myoglobin proteins leak out. When you have a heart attack, things called creatine kinase, little enzyme proteins, leak out of your heart and go into your blood. Proteins only leave when the cell dies. So what's the right answer here? 1, 2, 3, 4, or 5? Number 4, potassium leaves the cell during repolarization. Okay, that's the first section. Guess what you need to do by the next time I see you? Do the quiz online. So take lecture quiz number 1 online. The second folder is open for you, right? Okay, so you can see everything in folder number 2. You can see the slides and all of that. What? Take the online lecture quiz by Thursday. All right, let's start with lecture number 2. We've already set the background or the groundwork for it. Why did it not open? There it goes. So now we're talking about a neuron, and most of the things we're talking about with a neuron is actually that action potential. You can get an action potential with a muscle cell, but we're really going to focus on the neuron for the next week. Okay, so neurons, when you put them all together, they form a tissue with other nervous tissue, which are things like glial cells. We'll talk about those. You should know from your anatomy the parts of a neuron. How do you identify a cell body when you look at it under a slide? Look for the nucleus. There's a cell body, or the soma. The dendrites are doing what with signal? Sending signal away or sending signal in? In. It's bringing the signal into the cell. The axon sends the signal away from the cell body and away from the dendrites all the way down to these endings, which are called terminals. Yep. You have a terminal illness, it's the end. You have the terminal in a neuron, it's the end. The other location, if you don't remember from anatomy, is this axon hillock. That's the beginning of the axon. This is such an important area because that's where an action potential starts. Graded potentials are up here on the cell body, they're up here in the dendrites, but an action potential starts at the axon hillock. You already know this. Once initiated, an action potential is conducted through the axon. Can you get a big action potential going down that axon? No. Can you get a small action potential? No. Every time it has an action potential, it's always exactly the same. It looks exactly like that graph we just drew every time. It starts at -70, goes to +30, comes back to hyperpolarization, and then goes back to normal. All right? This is kind of important. There's a refractory period. After you get one action potential, there's a brief refractory period where you can't get a second one. So what happens, or why this is so that there's no way an action potential can move backwards down an axon. Unidirectional transport in an axon all the time, never goes backwards. If you want to send a signal from your fingertip to your brain, the axons are heading towards your brain, the signal always comes in. If you want to send a signal from your brain to your finger, what do? You send it back down that same neuron? Nope, you have a second neuron that's turned around the other way, and its axon points towards the finger. Because axons only send electricity one way, ever. A refractory period's kind of this brief hesitancy so that you can't get a second action potential. It can't backfire. It can't misfire. You can't have a flaw. But there are two types of refractory period. There's one that's called relative and one that's called absolute. So here this red thing is what you absolutely have to know. You have to know the red pathway. When you have this initial triggering stimulus, what's moving into the cell? Sodium. What am I trying to hit at about negative 50 here? Threshold. When I hit threshold, what happens to all the sodium channels? All of them open. Every one of them open. Can you get more than 100%? Not unless you're a gym coach, right? Give it 110, boy. That guy is teaching gym because he sucks at math, right? Moving on. But anyway, it's like that old joke, those who can't teach teach gym. I didn't get along with my gym teacher, if you could tell. Anyway, so all of them are absolutely open. This period right here, while everything is in an absolute state, 100% state, is called part of the absolute refractory period. Can you get more than 100% of those channels open? Absolutely not. It's part of the absolute period. Up at the peak, 100% of the sodium channels close. Can you close more than 100%? No. So is that absolute? Absolutely. The potassium channels, 100% of them open, going all the way down this refractory period. Can you get more than 100% open? Absolutely not. Is that absolute refractory? Absolutely. So that's how you remember these are absolute. There's absolutely no way you can change this pathway. This is like pulling a trigger on a gun. You can pull the trigger back just a little bit, but as soon as it clicks, can you take it back? No. As soon as you pull the trigger, you have an action potential. As soon as you hit threshold, you are committed absolutely to this rise and absolutely to this fall. Absolutely. It's when it gets back here to resting. Suddenly, when it's back at resting potential, some of those potassium doors reset. Some of the sodium doors reset. Are you in an absolute state anymore? No. You're in a relative state. You're not absolute anymore. Is it possible to open up those potassium or sodium doors again? It's possible. You could potentially get a second action potential during this relative state. So when you go into hyperpolarization here, some of these things are reset. Not all of them are reset yet, but some of them are. If you need another action potential for whatever reason, during the relative refractory period, you can get a second one. Can you get it during the absolute refractory period? Absolutely not. During the relative refractory period, sometimes you can. Let me tell you how a brain works. The brain is 100 billion neurons that are dumb. They're absolutely dumb. These neurons, they only know two things. They know on and they know off. They don't know how to wipe their own ass. They can't do anything except turn on and turn off. They have these glial cells that take care of them. They feed them, they nourish them, they protect them, they help them heal. Neurons just turn off and on. But the neurons are connected. All 100 billion of them are connected in such an intricate pathway that gives you the ability to think. But it's all by these series of off and on switches. Anybody know what that would be like in the computer world? Everything you see on a computer is based on what kind of code? Anybody know? Binary code. Series of ones and zeros. If you ever watch The Matrix and you see all those ones and zeros flowing through the background, that's what's going on behind a computer, is all these offs and ons. It's the pattern of offs and ons that tells the computer to make this picture, to allow me to put this as one color yellow and that as another color yellow. Your brain works exactly the same way. It's a series of neurons that put this big picture together by talking in off and ons. So let me give you an example. I used to do research in pain. If you hook up an electrode into a pain neuron, a lot of times you'll hear it firing. Real slow though. It goes tick, tick, tick. Every time you hear a tick, it's going on. Tick, tick, tick. It's kind of its way of saying, I'm still here, I'm still here, I'm still here, I'm alive, I'm doing well, I'm okay, block, block. But if I squeeze your finger, it goes tick, 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 tick. Did I do higher pitch ticks? Nope. What did I change? The frequency, good word. I changed the frequency, the distance between those ticks. Each tick is an action potential. I brought them closer. And then suddenly, I smacked your hand with a hammer. Guess what happens to those ticks? And it's your brain's way, or your body's way of saying, hey, there's something bad going on here. Look in this direction and move it. It doesn't know bigger ticks. It's like Morse code. With Morse code, you've got one guy pushing a button. Tick, 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 tick. It's not high-pitched ticks. It's not low-pitched ticks. It's just the matter of whether he's ticking or not ticking, and that's it. The person way down the telegraph line, they're listening. It's the tick, 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 tick. That's what your brain does. It listens to the patterns. It's the frequency. The absolute refractory period is a chance for you to, instead of going tick, at that point, you know the Morse code guy died and stuck his head on, right? That's the only thing that tells you. But the absolute refractory period is a chance for you to reset between ticks. It gives your brain kind of a reference point and says, okay, there's the first tick, when's the next one, there's a second one, there's a third, there's a fourth, and tells it the frequency. If this were always on, your brain wouldn't know what to do. It'd have no idea. The absolute refractory period is important for separating those action potentials and for only allowing one direction flow down an axon. So that way your axon doesn't blow up taking signals from both ways. It always moves from the hillock to the what? The end. What's it called? The terminal. Always. Hillock to terminal. Right? Other characteristics of an action potential, we call it the all or none because either you get it or you don't. You get a big one? Nope. You get a small one? Nope. You always get the exact same size action potential. Do you always get the same frequency of action potentials? Nope. That's what tells your brain what's going on. Okay, and then the strength of the stimulus is perceived by the frequency, which we just said. All right. Two ways of conduction. Two ways, not two directions. There are two ways to conduct this signal down an axon. You can do it locally, or you can do it by saltatory. The biggest difference between these two is speed and myelin. Local current flow, they call contiguous or continuous flow, is very slow. It's like walking across the room, one foot in front of the other, but connected. So you put your one foot to the toe, toe to heel, toe to heel, toe to heel, toe to heel. It sends a signal, one after another, all the way down the axon. Saltatory is like hopping. It jumps. It jumps from one node of Ranvier to the next. What's in between nodes of Ranvier? What's that lipidy layer wrapping myelin sheath? So local flow, continuous, step-like fashion, one after another, after another, after another, after another. Not fast. It always moves from the most positive area downstream. So if we're talking about starting at the axon hillock here, it goes here, to 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 here, all the way down, one at a time, like a chain of dominoes. Tick until it hits the terminal. As sodium flows in here, and this is kind of the tricky part, each one of these represents an action potential. There's one, there's one, there's one, there's one, there's one. This action potential will trigger the next one. This action potential will trigger the next one. This one triggers the next one. So when you look at the phases of an action potential, as sodium's flowing in here, right, and then it moves boom, to the next area, what's flowing in now? Potassium. Sodium flows, I shouldn't say in. Sodium flows in here, and then potassium turns around and goes back out. As long as potassium's going out, no sodium's moving. As long as sodium's going in, no potassium's moving. They switch. So as this one's going through its absolute refractory period, can I send this action potential backwards? Absolutely not. The absolute refractory period is always one step behind the active action potential. So it just keeps moving. Dunk, 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 all the way down. Saltatory jumps between nodes. Axon hillock, first node, second node, third node, fourth node, terminal. Way faster. The only reason it does that is because of myelin. In fact, the more myelin you put around an axon, the faster it moves between those nodes. So saltatory is step by step by step by step. Contiguous is step by step by step by step. Saltatory is jump, 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 done. Okay, what makes myelin? Oligodendrocytes. Where do oligodendrocytes make myelin? Peripheral or central nervous system? Central. Where do Schwann cells make myelin? Peripheral. Here's an interesting fun fact. Only one of these has the ability to fix itself. Guess which one it is? The ones in the periphery or the ones in the central? Think about it. If you get nerve damage, where would you rather have? Would you rather have it in your brain or would you rather have it in your arm? In your arm. Because there's a greater risk that it'll heal itself. Schwann cells can regenerate, oligodendrocytes can't. After the age of 2, oligodendrocytes lose their ability to make this little growth protein. It's kind of a safety feature because if they made this extra growth protein, you might develop more tumors, is what they believe why it turns off. What's interesting also is that your brain, the number of neurons that you have when you're born are actually more numerous than the ones you have when you're 40 or 50 or 60 or 20 or 10. Because at the age of 2, you start killing off neurons. No, not because you start drinking, but because they naturally start pruning. It's actually called dendritic pruning. You'll kill them off. The ones that aren't useful, you get rid of. But the ones that are useful, you start branching them. You start making them more powerful. You start putting connections together. You start seeing things. You start thinking these new pathways. And we'll talk about this more next week with the pathways. But you actually lose neurons throughout your life. Your brain has fewer neurons than you've ever had in your entire history. But guess what? You're smarter now than you've ever been in your entire history because you're better at using those neurons. Right? So myelin, remember, those little gaps in between are the nodes of Ranvier. When you're first born, you don't have very much myelin sheath. How fast are the signals? Not very good. They're more conductive or contiguous, local, whatever you want to call it. As you age, and that's, by the way, why you wet your pants and poop your pants when you're a baby, is because the pathway going from your brain down your spinal cord and into your GI tract and your bladder isn't developed. It doesn't have enough myelin sheath to have the control yet. Same thing with puppies and kittens when they poop and pee all over themselves. They don't have control. So here you can see this jump. Here you have an action potential that jump to the next one. This one's in its absolute refractory period, so it can't jump backwards. It always jumps in one direction. But it jumps, which means it moves slower or faster than contiguous. Way faster. The speed is determined by two things. One is that myelin. Is there myelin on that? How much myelin is another question you want to ask. The more myelin you have, guess what happens to the speed? Faster. Second is the size of the axon. If you have a little tiny garden hose like this big, and you turn the water hose on, and then right next to it, you have a fire hose that's this big, and you turn the water on, which one's going to have faster flow? Fire hose. The diameter of the fire hose is bigger. So neurons that have a bigger diameter axon get faster flow. The energy moves quicker. It flows faster. So we'll talk about this with pain. When you get pain signals, when you touch something really sharp, and you go, ow, and you pull away extremely fast, how could you describe those neurons? Would it be contiguous or saltatory? Saltatory. Would it be highly myelinated or very little myelin? Highly myelinated. Would it have a large diameter or a small one? Large diameter. What about, you ever had like a crampy feeling? You're like sitting on the couch and you're like, ugh. I feel like, ugh. And then the pain just comes on. Really slow. It just gets worse. What kind of neurons do you think those would be? Highly myelinated? Very little myelin. How about the size of them? They're small. And when you take a medication, does it magically kick in and take the pain away? No, it slowly turns back off too. They have slow signals. Speed's dependent on the size, the diameter, and the thickness of the myelin. So if I asked you a question like this, which is a true characteristic for local or contiguous current? How about one? Contiguous conduction is faster than saltatory. Heck no, that one's false. How about number 2? Local current flow can occur on axons that are myelinated or unmyelinated. Nope, the contiguous are unmyelinated. Number 3, local current flow jumps to the bare spaces called nodes of Ranvier. What jumps then? That's saltatory conduction, so number 3 is false. Number 4, contiguous conduction is a step-like fashion. Yes, one step after another, after another, after another. So our right answer is number 4. What do you know about regeneration already without looking at this? Which ones can regenerate? Schwann cells. Oligodendrocytes can't. Where are the Schwann cells at? Peripheral nervous system. Yeah, I thought it sounded like the same thing. Okay. Here we go. In fact, there's actually nerve growth inhibiting or enhancing and nerve growth inhibiting chemicals that control oligodendrocytes. When you're a little tiny baby, you have lots of the nerve growth enhancing. But after 2, you start turning down the enhancing and turning up the inhibiting. It directs the growth of these neurons so that they have this nice, tidy pattern. Well organized, very clean pathway. Okay. Axon terminals end on muscles, glands, or other nerves. When you're trying to control something, this one neuron, the longest neuron in your body starts at the tip of your tailbone and goes all the way to the tip of your toe. It can go all the way down to the toe and control muscles to control flexion or extension of the toe. It can go to a gland. You can have neurons in your brain, your hypothalamus, that reach all the way down to your pancreas. When you smell food, it starts releasing insulin. That's a gland. You can have neurons in your brain that go out to sweat glands and tell them, hey, it's really hot in here, start sweating. And then other nerves. It can be one neuron going to the next, to the next, to the next. And in one neuron in your brain can have 100,000 other connections. Literally 100,000 other connections all over the place. Your brain is like the most complex mind map ever made. Okay, so when it connects to something, we call it innervating. So when I say that a certain neuron innervates a muscle, that means that it's going to the muscle. Next major point, synaptic communication. Synaptic communication is a synapse that's between two neurons. It's a little gap, actually, between the neurons. So you've got electrical communication coming all the way down your axons. We'll say this is an axon going all the way down until it gets to the terminal, and then this terminal just hovers, kind of hovers above the next neuron. I mean, technically there's spider-webbing material that kind of ties it together like stitching, but they're hovering. So the two neurons technically don't touch each other. All right, the little chemical messenger is called a neurotransmitter, and it diffuses across the cleft. So does it take active energy to do that? Nope, it diffuses. It goes from the high concentration where it came from to a low concentration where it wants to go. All right, terminology you have to know from anatomy. So axon terminal, of course, that's the end. Synaptic knob is another name you have down there. A bouton is another one. It looks like button. Synaptic vesicles, those hold neurotransmitters, and neurotransmitters are the chemical messengers. So a neurotransmitter can be serotonin, dopamine, norepinephrine, epinephrine. Histamine can actually be used as a neurotransmitter. Glutamate, like the stuff in MSG, glutamate, neurotransmitter. Substance P, they're all chemical messengers, they're neurotransmitters. The cleft itself, so you release this stuff, this is all on the presynaptic neuron. How is it possible I can say pre-synapse? Pre means before the synapse. What do you know about all action potentials? They always move in one direction, right? So the direction they're moving, the first one that holds the action potential is the pre, then it hits the synapse. Chemical messengers carry that message across, and then the postsynaptic neuron, the one next, this one down here, the big one, receives the signal from the chemical messengers and then fires another action potential that travels down. Those are the major structures of the connecting points. Look, an event list. What should you do? Give it a star. Events that occur when an action potential in a presynaptic neuron is propagated to the end of the axon. All right. So one step at a time. You get an action potential that starts where? Where did the action potential start in an axon? The axon hillock, right? It's propagated, which is a fancy word for saying it moves. It moves from the axon's hillock all the way down the axon until the knob. I'm going to show you the picture and walk you through it. So here it's moving or propagating all the way down. They forgot the myelin sheath, but it's going jump, 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 jump. What kind of conduction is that? Contiguous or saltatory? Saltatory. So it's jumping. Boink, 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 boink. When it gets down here, by the way, what is going in and depolarizing the axon? Sodium. This changes. Now when you get down to the terminal, the bouton, this knob thing here, now it changes. Sodium doesn't go in. Now a voltage change happens to a calcium channel. That voltage change takes and confirms, conformational change, and pops open calcium. Look where calcium is at. Calcium is a little bit slightly more abundant out here. Where does it want to go? In. Right? The positive charge wants to run in. The calcium being abundant out here runs in. Calcium comes flowing in. When calcium comes in, it will actually stick to these vesicles that are full of neurotransmitters. So you have these little vesicles that are full of neurotransmitters, and the calcium, I always think of it, since it's sticking, it gets them really heavy, it weighs them down, and they fall down to the synapse where they merge with the membrane, and then they just open up and kick their neurotransmitters into the synapse. So there you have the neurotransmitter being dumped into the synapse, and you can see it up close. High concentration in the vesicle, low concentration in the synapse. Where's it going? Into the vesicle or into the synapse? Into the synapse. By what process? Diffusion, right? So what's the process of opening this vesicle? Something cytosis. Exocytosis, opening it and dumping it out and into the synapse, but then it diffuses across the membrane, passive movement, until it finds a receptor. A receptor is like a lock. The neurotransmitter is like a key. Is a lock specific to your key? Yes. It's specific to whatever that neurotransmitter is, and that neurotransmitter fits perfectly into the lock, turns the lock, and just like in your door, it unlocks this doorway and lets the door open. Now you can either have ions moving in or ions moving out. If it's going in, what ion is it probably? Sodium. We're back to the beginning. Now we're starting over the whole new action potential. So sodium rushing in. If it's coming out, what ion is it probably? Potassium. Potassium going out of the cell. It doesn't always, that's why they don't label these. It doesn't always have to be sodium or potassium. It can be, or it doesn't have to be sodium every time. It can be potassium. It can be chloride. Doors sometimes can open. This is a generic pathway. So when you look at this, all the way down here, binds to a specific ion channel, sodium or potassium, whatever, or it could be chloride, we'll see later, leading to an event that excites or inhibits the next neuron. Here's your pathway. Okay, some synapses excite, some inhibit. Excitatory synapses, if it's excitatory, it's always excitatory. If it's inhibitory, it's always inhibitory. So excitatory synapse means you bring sodium in. What's sodium going to do to that next neuron? Depolarize it. Sodium rushing in depolarizes. It gets that next neuron excited. It's trying to hit what number or what level, dotted line, threshold, that negative 50. It's trying to excite it to negative 50, get to the threshold, and get an action potential. If it's an excitatory synapse, it is always an excitatory synapse. If it's an inhibitory synapse, it opens up doorways and lets one of two things flow. It'll let potassium flow. Where's potassium want to go if you open a doorway for it? Out. What's it do to the cell? It doesn't depolarize it. It doesn't repolarize it. It does what to that cell? Hyperpolarizes it. If you have negative 70 membrane and you pull out 10 potassiums, it makes it negative 80. You hyperpolarize the cell, which means you took it what compared to threshold? Closer or further away? Further away. Is it going to be easier to hit threshold now? Harder. It inhibits that neuron. It keeps it from hitting threshold. It's trying to shut it off. When you take an opiate, a painkiller, what it's doing is it's trying to shut off pain neurons. So would it be activating a potassium channel or would it be activating a sodium channel? Potassium. It's letting potassium flow out, hyperpolarizing that pain neuron so it's harder for you to feel pain. Can you still feel pain when you're on an opiate? You can. It's just harder to do it because it's harder to hit threshold. Another thing that can happen is chloride right down here. So it may not be a potassium, it may actually open a chloride channel. If chloride channels open, chloride goes in. If I open 10 chloride channels and I bring 10 chlorides into the cell, it takes from negative 70 to negative 10 negative charges added to a negative 70. What's negative 70 plus negative 10? Negative 80. It made it what? D, re, or hyperpolar? It made it hyperpolar, just like potassium. They do the same thing. They're both inhibiting that neuron. So technically, for future reference when you go into pharmacology, an opiate actually opens a chloride channel. Chloride goes rushing into the cell and stops the cell from firing. Next, when we talk about pathways, we'll talk about pain and shutting off pain. We'll talk about when the dentist doesn't want you to feel pain, he stops the axon. He blocks sodium channels on the axon, so sodium can't do what? It can't rush in, and it can't allow what? Inhibition or excitation. It doesn't allow it to be excited, so that signal stops right there. It doesn't go to your brain. Your tooth is screaming. It's in so much pain when he's digging around, drilling. Right? Makes the hair in the back of your neck stand up, doesn't it? When he's drilling in there, your tooth is screaming in pain, but the brain never gets the signal because it blocked excitatory. It blocked the excitation. So here's an example. Sodium comes rushing in. I depolarize. I get an excitatory postsynaptic potential. Is this a graded or an action potential? Is it an action potential? How do you know it's not an action potential? Yep, didn't hit threshold. Didn't follow that same pattern. So this is a what? It's graded. Can you get a small graded potential?
Yeah.
Can you get a big graded potential?
Yeah.
Yep. As long as it doesn't hit what? Threshold. Anything in here. So here's a graded excitatory postsynaptic potential. Here's an inhibitory one. Also graded. What would happen if I fired an excitatory and an inhibitory at the same time? It would look like this. No change. If I try and excite a neuron and turn it off at the same time, you get no change. All right. So every time you do one of these synaptic changes, it's a slow process compared to electricity. Action potentials, the axon goes, whew, sends the electricity down really fast. But when you're talking about moving neurotransmitters, they have to slowly diffuse. It's a little bit longer. Don't get me wrong, it's still a few milliseconds, but it's definitely longer than electrical conduction. So why this is significant, your brain has hundreds of billions of neurons, right? If they're all connected and there are 100 neurons in a row compared to 2 neurons in a row, which one's going to send the signal faster? The 2, because there's only one synaptic delay. The one that has 100 has 99 synaptic delays between it, so it's going to slow the signal down. The longer this pathway, the slower the signal gets because of synaptic delay. I already said this, though. Each synapse is either excitatory or inhibitory. If it's excitatory, the neurotransmitter is typically going to be glutamate. Glutamate is an amino acid. It's teeny, teeny, tiny. What did Fick say about the speed of diffusion or the speed of movement of a neurotransmitter that's teeny, teeny, tiny? Its rate is fast. If I look at this one, it's gamma-aminobutyric acid. The name tells you this is a big, fat molecule compared to glutamate. Is it going to be fast or slow? It's slow. Glutamate is a fast-acting neurotransmitter, excitatory neurotransmitter. Glycine is the same size as glutamate, but it inhibits. Is it going to be fast? Yes, these two oppose each other. Glutamate's fast to turn things on. Glycine's fast to shut things off. GABA is slow to turn things off. You don't have to remember the whole full name for it. GABA is just fine. All right? So some neurotransmitters are have an exclusive job. Glutamate always turns things on. Glycine always turns things off. GABA always turns things off. Others can be both, like norepinephrine. What's norepinephrine do to your heart? Turn it up or turn it down? It excites it, turns things up. What's it do to your GI tract? Slows it down, turns it down. It inhibits it. So that neurotransmitter, if it's dumped onto, we'll say muscles in the GI tract, it inhibits those muscles. If it's dumped on muscles in the heart, it excites the muscles in the heart. Right? So depending on what the synapse is, where it's going to, it can vary. What happens during an excitatory postsynaptic potential? Before even looking at the options, what's an excitatory doing? Trying to trigger excitation or shut it off? I said that wrong. An EPSP. E is excitatory, right? Try to turn it on. What ion do you want to look at moving? Don't look at the options. What ion should be moving? Excitation. What are you trying to do? Hyper, repolarize, or depolarize? Trying to depolarize. What ion do we keep giving credit for depolarization? Sodium. So if this were a test, the first thing that pops in my mind is sodium is moving. What can I do right now with that question? Calcium, sodium, chloride, sodium. Guess what? I can get rid of number 1, I can get rid of number 3. Now it's down to one of these two. Which one sounds more right? Sodium channels open up, and sodium comes into the cell? That sounds right to me. How about sodium channels open up and sodium leaves the cell? Guess what? There's another tip for test taking. Those are direct opposites. You know one of them has to be wrong, absolutely wrong, right? So you can eliminate it. This one's right. Sodium comes into the cell, excites the cell, and then you get that excitatory potential. That's it. We have, I think, 2 minutes left. I'm going to have you sign out on your way out the door so that I know that you were here. I'm going to walk right by you. You're excited to sign. You're going to walk out. I'm going to turn by the door so that you're signing out. You're signing out. What do you have to have done before we come in Thursday? The quiz.